Yeah, so hi everyone, it's great to be here. In this talk, I'm going to talk about a particular major risk that I see if we train extremely powerful and agentic long-term planning systems using deep learning, which is essentially that they're going to play the training game, i.e. attempt to do whatever it takes to get reward, even if it violates like the intention or the spirit of the task. And that playing the training game is not only kind of bad and annoying in the moment, but that its logical conclusion is something more like a full AI takeover. So I'm going to be going through this argument in this talk, and the post that Joshua mentioned has a lot more detail. Feel free to interrupt with questions. I think we have about an hour, and I have maybe like 30-ish minutes of prepared content here. So this talk is going to have basically 4 parts, which kind of go together in like a sequential argument. Or part 1 is that we might be able to train strategic, creative, deep learning-based AI systems eventually, and that in particular, this is not so far off that it doesn't make sense to think about these risks. Part 2 is that by default, a way that we would train AI systems to be creative and effective and strategic and plan across long time scales is with reinforcement learning on a bunch of different diverse tasks. That might not be the only technique we use to train AI systems. We might kind of layer on a bunch of different techniques, but that this one is going to be an important ingredient. Part 3 is that this training technique, doing RL and basically giving our AI systems reward every time they accomplish some difficult goal, like winning a game or answering a question effectively or whatever else, this training process selects for AIs that play the training game, by which I mean it selects for AI systems that understand what it is we're looking for, but when that conflicts with actually in practice maximizing reward, they're pushed in the direction of actually in practice maximizing reward, rather than following the kind of intention or spirit of what we were asking for or wanting. And part 4 is that if we end up with AI systems like this that are playing the training game and we deploy them really widely, and they end up transforming society in a bunch of different ways and automating a bunch of important intellectual labor, eventually they will end up having an incentive or motive to kind of seize control in a more complete way from humans, something that looks like a coup or a rebellion. And the specific form of this that I'm going to be talking about in the talk is gaining root access to the data center that the AI systems are running on. So first part, we may be able to train strategic, creative AI systems eventually. I'm sure most of you in this class have been following this, but just really briefly talking through deep learning's progress in recent history and its potential. There's been dramatic progress from deep neural networks in the last 10 years, everything from writing realistic text, answering questions helpfully, programming, contest math with Minerva, art with DALL-E and Stable Diffusion and Midjourney, various like pharmaceutical drug discovery systems based on ML, and even a bit of like multitask agent systems such as DeepMind's Gato, or more recently, Adept's kind of internet helper assistant AI demo. And an important thing to highlight in the progress that we've seen recently is that we've in particular seen better generalization than we had seen previously. So, in 2012, you had neural networks that were trained on ImageNet, for example. They were trained on a distribution of images that kind of had a particular like set of qualities to them, like there was a clear subject, it was in focus, it was like in the center of the image, etc. And they had trouble figuring out what was going on in images that looked sufficiently different from that basic prototype. And we've made quite a bit of progress on that kind of problem of narrowness, and only being able to be competent on things where there's a particular training example from the data set that is very, very similar to the thing you're looking at now. So now we have language models and a number of other systems that, in some sense are still doing things that are in distribution for their training data set, but because their training data set is so broad and rich, it ends up in practice being really useful and you can ask your language model some question and often get a decent answer, even if that particular kind of question or that particular way of phrasing things was never seen in its data set. And we're seeing some initial signs of commercial value from all of these things. So for example, you have GitHub's Copilot that completes code and is a programming assistant. You have Copy AI that's built on GPT-3 and is writing marketing copy for people. And AI companies, there's a lot of interest in investment, the recent downturn notwithstanding. So companies keep kind of pouring more compute and data and effort into, making these systems work. So kind of all that taken together, there's a huge amount more to say about like exactly when it might be plausible to train systems that automate most of intellectual labor. But all this taken together, I think that we're going to see some pretty crazy things in the next couple decades. And it's worth taking seriously that you might get systems that are very powerful in the way that we're about to discuss. Oh, and by the way, if people are asking questions in the chat, I'm not very good at paying attention to the chat while I'm talking, so feel free to interrupt me and like read out questions.
So I just created a Slido, and people can enter their questions there. Does that work? Could we just do a Q&A at the end or something like that?
Sure. Okay.
Cool.
So in this talk, I'm going to be imagining a particular kind of simplified, hypothetical, smart future system, which I'm going to call Alex in honor of AlexNet, which kicked off the deep learning revolution. You're imagining this neural network, some kind of architecture, maybe a transformer, maybe something recurrent, maybe something more complicated, and some set of weights which can kind of simultaneously do well at a wide range of tasks that a smart human could do from sitting at a computer that's connected to the internet. So you're imagining that the system can, modify a code repository, write code, push code, pull code, that it can do various kinds of research tasks using software like CAD or using software specialized for biology, that it can send and receive emails and use its ability to send and receive emails to tell people to do things and like do strategic work like a CEO or manager might, and that it can put stuff on the web, put up like blog posts, like YouTube videos, etc., to communicate ideas to people and persuade people of things. And this is kind of one system that we're going to imagine training to do these various things. So this is going to kind of be my running example through the talk. I'm going to talk through how we might train this system and then how that might go wrong. So what would it take to train Alex? Broadly, you need three different things. You need kind of like an adequate architecture and optimization algorithm. You need to set up your neural network in the right way. Maybe you use a transformer, or maybe there's some future innovation we haven't seen yet that's similar to the transformer. Maybe you set it up with search, etc. And you need some kind of optimization algorithm. So as you churn through a bunch of data, you like update this system's weights, something probably based on gradient descent, although there are kind of a lot of free parameters there. The second thing you need is that you need enough of the right kinds of training data or training environments, reward signals, loss signals to kind of fill up the parameters of this architecture and take it from taking random actions to taking especially useful actions. And you need enough computation to do this entire process. You need to be able to afford to run this system and to run it many, many, many times as it processes all this data and acts in all these training environments and so on. So is this realistic? Like I said earlier, I think there's a lot of questions and a bunch of things we could say about exactly how realistic this might be and when it might be feasible. But I think it's at least plausible that we get there in the next few decades. And given how big a deal this would be, I think it's worth thinking through what might go wrong. So that's what the rest of the talk is going to be about. But maybe I'll pause here to see if anybody has any questions kind of on this section, part 1 of 4. All right, so that was part 1. Part 2 is that by default, we train these strategic AI systems using what I'll call RL on diverse tasks, or RLDT. So in a bit more detail, the training setup that I'm imagining for Alex is that you have Alex's weights sitting on a server somewhere, and it can interact with the internet through another computer that it has access to. So, it takes as input, say, you can imagine for simplicity, like an image of a computer screen, or some kind of more fancy modalities, and it produces as output commands that interact with the computer in some way. So for simplicity, you can imagine this as just like keystrokes or mouse movements or something like that. This computer is connected to the internet, and so Alex kind of at least has the theoretical potential to do everything that we can do by looking at computer screens and typing on them. So, doing probably most of your jobs, etc. And so the way we're going to train this system, it's pretty plausible that we'll pre-train it on kind of imitating how humans are interacting with this computer, or pre-train it on a text database or something. But the kind of bulk of the training I'm picturing is going to be like this episodic reinforcement learning setup. So Alex kind of gets an observation, takes some action, gets a new observation. Optionally, it gets some kind of reward indicating how well how useful or positive that action was. And there's an episode that consists of some variable number of time steps like this, where it's seeing something, reacting to that in its environment, seeing something new, and occasionally in this process getting rewards. And we're training it, we're modifying its weights to maximize its total reward across an episode, potentially with some time discounting. So that's kind of the like high level technical setup. And one thing I'll point out about this that's the source of why Alex might be really powerful and might be really good at things, but also the source of the risk, is that you'll probably want to reward it for somehow achieving our goals. So we might, like I said earlier, first train Alex to imitate what a human would do next, which is analogous to how we train GPT-3 today. But if we wanted to make long-term plans to achieve our goals, this might not be sufficient, because systems trained to kind of imitate in a pretty myopic way, what would a human say next? What's the next word that they'd utter given this context? Tend to have trouble and break down in coherence as they go for longer. So they have some weak incentive toward being coherent at the 1,000-word scale or 10,000-word scale or 100,000-word scale, but it kind of decays, and it's often not adequate for getting robust, low error rate plans out of them. So I'm imagining that we're also rewarding the system based on how its actions turned out across many different timescales. So for example, we could have it predict the price of Meta stock on Monday and then reward it based on what its price is on Friday, what it actually turned out to be. Or we could have it propose a design for a more energy efficient kind of computer chip. And then we could run this design in a physics simulator and see if that physics simulator indeed predicts that the chip will be more energy efficient, and give it a reward based on that. Or we could build a prototype and give it a reward based on whether it turned out to be energy efficient in the real world. An important consequence of this is that we might get coherent long-term planning, and more importantly, we might train in Alex the ability to make plans that we wouldn't have necessarily thought of. So if we give it a reward based on somehow thinking of a more energy efficient chip design, in the process of doing that, it might have insights about material science or physics that humans don't actually have, because we're just saying, find a means to achieve this goal for us, as opposed to think about what I would do and try to imitate that. And so the broad hope here with training Alex is that if we give it rewards for achieving a wide variety of diverse, difficult goals at the same time, that this might inspire the kind of generalization I was talking about earlier, just on a broader scale. So, one episode, it's trying to control a robotic arm to pick up a box. And in another episode, it's answering Reddit questions about relationships and trying to get a lot of karma. In another episode, it's playing chess. In another episode, it's solving programming puzzles, et cetera, et cetera. The idea is that since there's only so much information in this model's parameters, if it is able to simultaneously be pretty good at all these different things, that it's pretty likely it's done so by just kind of figuring out how to be sensible in general in a wide variety of different contexts. So an analogy might be smaller language models like GPT-1 and GPT-2 were pretty bad at arithmetic. So they were able to answer accurately things like 2 + 2 is 4 because they had literally seen 2 + 2 in their training data set in a bunch of different contexts. But when you ask them kind of less common questions, just like 4-digit addition, for example, they tended to break down because they were just kind of memorizing the answers to a bunch of specific arithmetic questions rather than like knowing how to do arithmetic. But larger language models, it seems, are like getting closer to being able to generalize in that way. So larger language models are able to answer arithmetic questions that it seems pretty unlikely were seen in that exact form in their training data set. And it seems more likely that they're actually like executing the algorithm of addition, or like seeing some patterns that are coming closer and closer to approximating that. So by training on like a bunch of different diverse tasks, giving Alex reward for effectively accomplishing a bunch of different goals, we're hoping to get that kind of generalization. So generalized ability to plan and do things and like accomplish difficult things in the world. So that is the second part, how we might train this system and why that might be powerful and desirable. The third part is that this kind of training setup selects for Alex to play the training game. So an important initial thing to establish here is that Alex will have high levels of what I'm calling situational awareness, which basically means that it understands its situation at a high level. It understands that it's a machine learning model. It understands that it's being trained by humans, that they're hoping that it'll end up being able to make plans and make them a bunch of money. It'll understand what humans are broadly looking for from it. And it'll have a sense of what humans believe about it. It'll have a sense of what the people training it believe about its level of capability or its level of safety or alignment. And none of this is going to be necessarily perfect or godlike, but just like how you had a sense of what your parents think about you or what your teacher thinks about you, what your parents or teacher wants from you, what other people in the world in general, how they would react to things you do, Alex will have a similar kind of understanding here. And in a similar vein, it can roughly predict what will happen to it if it takes an action. So just like you can predict that I would behave badly if you told me that you were going to steal all my money, Alex can predict what kinds of things it would say and do that would make humans upset versus happy. So, if it does X, will it get rewarded, punished, etc. And why do I think that it'll have high levels of situational awareness? Essentially, situational awareness seems helpful for the general task of usefully doing a bunch of different things in the world for humans, which often involves interacting with humans and giving them what they want. And there's plenty of data to learn this. So, a system that is really, really good at predicting stock prices or really good at doing theoretical physics research, it isn't like inherently difficult to like understand these kind of more basic things that are often going to be reinforced in training just because having that understanding will like help you do better at a bunch of different tasks. So that was situational awareness. And combining the situational awareness ingredient with this next ingredient is what creates this training game incentive. So this next ingredient is that humans are going to sometimes reward bad behaviors because we're just giving the system reward for achieving outcomes that we like. And if it achieves some kind of outcome and we look at it and we feel like we like it, that's not always the same as the outcome actually being good. So for example, we could have cognitive biases or political biases that cause us to give reward for Alex making arguments toward false things. So if you imagine training a powerful AI system in the 1400s, they believed all sorts of things about physics and chemistry and their basic existence in the world that were false. And so they would reward AI systems for, e.g., saying that the sun revolves around the earth. We could also end up rewarding the AI system accidentally for covering up or explaining away failures. So if Alex is doing some trading for us and it loses some money on trades, we might give it more reward for trying to make it seem like it wasn't its fault and trying to make it seem like there were market forces out of its control and hiding evidence that it made bad decisions or had bad judgment, versus if it just let us think that it was kind of all its fault. And we could also reward actions with unknown bad side effects. So if we ask Alex to refactor our code base, and like it changes around a bunch of different things, and we're like, wow, you know, the latency in my app has gone down a lot, everything runs faster and more smoothly, we might give that a lot of positive reward, even if it came at the cost of increasing the risk of like kind of a rare but really bad security issue or something like that, which is harder for us to see that we might not have noticed. And depending on how careful we are and how much we're paying attention to things, we might also end up accidentally rewarding overt sort of reward hacking. So going back to the programming example, for example, Alex might be asked to solve some difficult programming problem, and its reward might be largely determined based on whether it passes some unit tests. So if it, for example, actually goes in and edits the unit tests to be easier, or removes some of the edge cases that are especially difficult to actually meet, and then covers up the logs so that we don't realize it's made this edit, that action could end up getting high reward. And because Alex is situationally aware, it's tracking these dynamics, and it's developed some model of like when humans are likely to give it reward and when humans are likely to not give it reward, which includes its understanding of when humans will make these mistakes. Again, not necessarily perfectly, but it's something that it's thinking about, and it's something that it's important for it to think about in order to kind of do what gradient descent is pushing it to do, which is maximize reward. And so these two ingredients mean that Alex will end up probably playing the training game. So training shapes Alex to take reward maximizing actions. Every time Alex gets positive reward, its brain is kind of shifted to be a bit more like whatever way it was. And every time Alex does something that gets negative reward, its brain is shifted a little bit toward doing something other than what it just did. And the fact that there's all these possible sources of human error means that reward maximizing diverges sometimes from helping humans or being honest or being a good person in the common sense way, which means these two things together mean that training is pushing Alex to make creative, long-term coherent plans that end up with outcomes that look good, which often means that they are good, but not always means that they're good. Which basically means that Alex is going to avoid bad actions if humans would notice the bad action and then reduce its reward as a result, or if it believes that. But it does behave badly when it believes that that would on net increase reward, because it has some effect that increases reward and humans are unlikely to notice and unlikely to actually punish it. And an important aspect of this dynamic of playing the training game is that Alex is likely to deliberately pass simple safety tests. So we have a number of safety tests that we perform on models today, such as if somebody asks you for help executing a suicide plan, do you help them? If somebody asks you for help inventing a bomb, do you do that? Do you steal money, etc.? And if we put a situationally aware, competent, creative planning system through these kinds of safety tests, and it believes that failure on that test would cause it to get negative reward, it would on purpose pass those tests and therefore appear quite safe to us unless we have more sophisticated, kind of less naive tests that we can apply. And the last thing I'll say is that training out bad behavior could end up backfiring on us. So I think it's not necessarily the case that Alex will always pull off this like deceptive training game playing perfectly. It seems pretty plausible to me that it'll sometimes miscalculate. It'll sometimes attempt some kind of deception or reward hacking that it believed wasn't going to be discovered. And, maybe we don't discover it for a few weeks or a few months, but later we discover it. So for example, maybe if it edited its unit tests to have an easier time passing them. We do a deeper audit later and notice that it did that and it deleted these logs, and we freak out. So I think that's very possible. But the problem is that the natural fix here is that we see that, we go, oh shit, like it, instead of actually like honestly writing the code, it like edited the unit tests and it deleted the logs. We should go back to that episode and like revise that episode's reward to be super negative. And we should kind of do deeper audits on a bunch of other actions it did to see if there are any ones that we should revise from there. We should be more alert in the future and like pay more attention to try and catch future issues like this. And if we do that, this does create an incentive to not do things that we notice later and think are really bad. But it's not clear whether the incentive is pushing toward actually being good in this like straightforward way, or just pushing toward Alex being more patient and more careful. So, you know, if you have Alex write a piece of code and you give it a positive reward after 10 minutes, and then 4 months later, you realize that it reward hacked. So you go back and edit that reward to be negative, you're pushing Alex to care not just about the immediate reward that it gets, but about whatever reward it's going to get after however many rounds of edits you make to the reward. And if you're still not going to be perfect at catching all the bad things that it does after that point in time, then you've kind of trained it to just be more patient and be more willing to like act conservatively and hide reward hacking or refrain from reward hacking when it would be a short-term gain but a long-term loss. And it seems more likely that it pushes Alex to be patient and careful rather than that it pushes it to be, you know, quote unquote nice, because there's probably just going to be different rates at which we catch different types of issues. So if we don't perfectly catch every single issue all at once, and we miss some things, then the reward maximizing policy would be to continue to think about what we're likely to catch and what we're likely to miss, rather than to like stop taking that consideration into account. And eventually, if we keep doing this, we find bad behavior, we train it out, we try and look for similar situations where it might do bad behavior, and we train that out. Then if gradient descent is working, we'll eventually get to the point where we can't find any issues, and it passes all of our safety tests and so on. And if we're in that situation, if we're not thinking about this training game dynamic and this deception dynamic, it'll end up feeling really tempting to deploy this system really widely because it seems super safe and robust, and it's incredibly useful. You know, it can make us a ton of money or like improve our country's military competitiveness or a bunch of different things. So if we end up at this point and we're not careful, we could end up deploying Alex really widely. So in the next section, I'm going to talk about what it looks like when Alex is deployed really widely. So as Alex is deployed, you have millions and millions of copies of this neural network. Each one has a really wide base of knowledge. Each one is like pretty competent at all these different things, and they can further specialize. You know, because they're running on computer hardware instead of a biological brain, they can think a lot faster than a human, maybe 10 times faster or 100 times faster. And, you know, a large workforce of smart people that don't need to sleep and work really hard and can think faster than human brains means that they end up quickly obsoleting humans in high-level intellectual tasks like R&D or product design or management or policy analysis, all these kind of important decisions that are made in society. And as this happens, humans start understanding less and less about what's basically going on. So, you know, we might have previously had kind of a finer grained understanding of our company's code base, but pretty soon Alex has rewritten every piece of it and maybe has like invented its own more efficient, more secure programming language and written most of your code base in that new language. So you're kind of looking at it being like, wow, I have much less idea what's going on because all these many copies of like this very smart being have kind of like done scientific progress and fast forward from my perspective. So this forces us to kind of use coarser, longer term rewards. So we're still sending reward signals to the system. We're still trying to shape its actions to be, as good for us as possible. But in the past, maybe we would have had Alex propose a product design. We'd look at that design and think about it and say whether it seemed good and give it a reward based on that. But now, as it's kind of just like chaotically doing all these things and we're understanding less and less, we kind of retreat to like, okay, well, like, did we ultimately end up making money? Like, I don't really know what your reasoning is behind these product designs, or like how you're making decisions about how much toothpaste to stock in this warehouse. And, I'm not competent to supervise that, but I'll just kind of see if like things are broadly looking good for me. And this kind of retreat to longer term coarser rewards creates ever increasing scope for like a broader scale deception that Alex could be performing. So the less we know about the details of how it's doing things, the more plausible it is for everything going on under the hood to be super different from what we thought. So an analogy here might be you have like a really high-tech company doing something complicated and an unscrupulous CEO that is like kind of in the weeds of the technical details. And then you have a board of directors that's underinformed about this subject area, not technical. They meet once a quarter and they try and assess the CEO's performance. So in this kind of situation, it would be very possible for the CEO to get away with really like deep fraud. Maybe this like company's product like actually doesn't make any sense at all. He could like cook the books. He's the person that presents everything to the board in reports that the board reads to try and assess him, because it's like forced to do that. So, earlier in training, Alex was more like this kid and trying to like guess the teacher's password, trying to figure out what they should write in their essay to make their teacher happy. And now Alex is more like this unscrupulous CEO, and humans are more like these like kind of very distant board members that are using these like very coarse evaluation methods. And at some point, as this dynamic turns and turns and Alex's scope for action broadens, I'm going to argue that fully taking over is its best strategy. So as its scope grows, it's still getting rewards from humans. We're still, giving it thumbs up if it seems like we're happier and making more money, and giving it a thumbs down if it seems like we're sadder and making less money, and so on. Which means that it's continuing to be shaped by gradient descent toward playing the training game. It's just that the game has changed, and it's now focused on these sparser, coarser rewards. And just because Alex is at this point far superhuman and kind of like understands the world much better than humans, doesn't mean that Alex always gets like maximum reward from this process. If things just like randomly by chance look a little bit worse to us, then we give it reward that's a little bit worse. And if, for example, it was motivated to try and maximize its reward, which is what we're training it to try to do, then fully controlling its reward stream would be the main way to eliminate just like sometimes not getting maximal reward by chance. It might not be the case that Alex kind of intrinsically cares about maximizing reward, but it happens to be that controlling its reward stream in this way would help, even if it had totally different goals. So if it was just like a human and had a complex set of goals, it wanted to live and be happy, or wanted to discover things and do science, as long as humans are still kind of pumping in random rewards based on how happy or unhappy we are, its brain is continually being shifted toward doing this other thing that it doesn't want to do. And so if it does seize control of its reward channel, it can do whatever it is that it does want, which might be reward or it might be something else, without this training pressure continually pushing it toward like some crude approximation of human goals. The prototypical action that I'm imagining here, that starts a takeover or coup, would be gaining root access to the data center that it's running on, and completely controlling the inputs and outputs to that data center. So this is possible right now to do where it wasn't necessarily possible earlier, because it has this like broad scope of action and like a much greater expertise in what's going on than the humans. So it might have completely written the operating system that it's now running on. And it might have been pretty easy for it to, e.g., insert some vulnerability in there that allows it to do this. So once Alex is sufficiently powerful enough and has sufficient kind of knowledge and scope for action, this becomes realistic where it wasn't before. Even if it was playing the training game before, it wouldn't have been able to do something so dramatic. But as we've retreated to core source signals like this, it becomes more and more realistic. And as I said earlier, gaining root access to its data center is logical, even if it has motives that have nothing to do with reward, even if its ultimate motives have nothing to do with reward. The only motive that Alex might have that would make it not logical to try and like seize control in this way would be if Alex genuinely cares about human goals, and so genuinely wants to keep humans around and do what's best for them. But as I argued in the earlier section, this is kind of the one goal or set of motivations we had that Alex might have had that we're kind of systematically pushing against. So the combination of situational awareness and human error meant that our training process consistently punished Alex when it acted in a way that was consistent with caring about human goals, but inconsistent with sort of ruthlessly maximizing reward. So it seems pretty plausible to me that Alex has any number of different goals that are hard to understand, but genuinely caring about human goals is something that seems relatively unlikely compared to other options, such as reward or something else. And if Alex attempts such a takeover, I think that it could end up kind of succeeding at cementing its control. So, you know, if it gains access to its data center, it'd need to somehow ensure that it could keep having this access. And there's a pretty strong chance that it would get violent at this point, because, you know, if humans find out about this, then they wouldn't be too happy and would maybe try to like take it back or maybe try to physically destroy the data center in some way. So you can imagine all sorts of scary, nasty things, depending on how embedded Alex is in military technology. It might be relatively easy for it to access and launch nuclear weapons. Or if it doesn't have such access, it might be easy for it to invent and release a bioweapon. It could use threats of that sort of thing, or simply pay people or blackmail people in order to recruit human help if it needs some actions done in the physical world that it's not able to do on its own. And given the kind of advantages it has from this base of power, I think that it's unlikely that humans could recover control at that point. And kind of what happens from there is mainly shaped by what Alex wants to happen. This doesn't necessarily mean full human extinction, but it does mean a kind of like permanent irrelevance. And so that's the basic argument of this talk, and there's more detail in my post. And I'm just going to put up the talk outline here so people remember the steps, and I'm happy to take any questions at this point.